Just to kind of clarify something, exam 2 will be a week from Thursday, so that hasn't changed. But what has changed is I'm not going to cover 3.4 on exam 2. So originally I said we were going to cover 3.4, but with the snow days and implicit differentiation, logarithmic differentiation, I definitely want to go over any questions you guys have over 3.1, 3.2, 3.3, kind of today, beginning of class. And then I'll get to 3.4, but I won't finish it until Tuesday. So for you guys to hand in homework over that on Friday and get any kind of feedback is a little tight. So I'm going to take off 3.4 on this next exam, so that means your written homework's only going to cover up to 3.3. So we've covered all that.
Is it going to be the same thing as the second quiz? Is that just going to go 3.3?
Correct. Yeah, so 3.4 won't be on the quiz on Thursday as well. So we have a quiz. Tomorrow I'll give you a quiz in class. I'll also post it on Blackboard, and it will be due Wednesday in class. So you'll bring it to class on Wednesday. And then Thursday we'll have an in-class quiz, just like the first couple of quizzes. And that will catch you up. You will be quizzed over all the material that will be on the exam. So you'll have an idea of what kind of questions I'll ask.
So the take-home quiz is over what? And then
The take-home quiz, I think it's 3132. It was in that email. I think 3132. And then the in-class quiz is 3.
I think it's
3.
3.4.
Yeah, so it might be 3233. I might ask some more questions that was on that take-home quiz as an in-class type quiz. So 3132 and 33 will be covered over the take-home quiz and the in-class quiz on Thursday. Take-home quiz, I'm expecting you to spend more time on it than I give you in class, so it might be longer, but it'll still only be worth 25 points. Where the in-class quiz will be, okay, this is what I expect you to do within 5 or 10 minutes of class.
What about Wiley Cluster
3.4 on Wiley, I mean, it's still going to be due. I can extend it past the, I think right now it's set to be due the 11th. I can push that back to the next Monday. But however, we'll still cover it and it'll still be due eventually. So pushing that back is perfectly fine. Okay, does anyone have any questions on Wiley? 3.1, number 1, has an error, and I submitted the error earlier this morning. However, they haven't got to it yet. If you put in negative exponents, it doesn't like it. It should like it. It should accept it. So if you put a negative exponent and it is the correct answer, it's just not in the exact form they want it. If you put like something minus x to the minus 2, they want minus 1 over x squared. You can spend your time getting it to the form if you want. However, Wiley will fix it, and Wiley will regrade it and give you your points back. So I've had some students email me, and I just gave them the points back at the time, but I also submitted the error. So Wiley should get to that relatively soon. All right.
Is there, on that same assignment, so the third or fourth one in has...
Second derivative?
No, it was a function equals, and it was like 258 times x squared minus y squared. Is there a easier way to do that one than just multiplying it out and then simplifying all those terms?
Yeah, you can use the chain rule and the product rule and hold them together and differentiate it and then plug in 5 and 1.
All right.
Do you guys want to see this one? Yeah. Okay, so the idea behind it, as long as you're following through the derivative correctly, simplifying dy dx, you can leave it as factored or not factored if you want. Sometimes factoring it, or sometimes not factoring it out and expanding it leaves you for small errors, like when you go to plug it in. So I have to plug in x equals 5 and y equals 1, and the more compact that is, the easier it is to plug in and plug that into your calculator. So let's look at this problem. This is 3.1, number 27. So we have 6 times the quantity x squared plus y squared. I'll switch it over as soon as I get the problem written down. And I want to find the slope at 5, 1, slope of tangent line. So the slope of the tangent line is the value of the derivative at the point. So I have an x point and a y point. So differentiating this with respect to x, so I have, so this is a chain rule problem. I could expand it out because x squared plus y squared squared is not too difficult. But if it was x squared plus y squared to the 5th power, you wouldn't want to waste your time expanding that out. So this is going to be 12 x squared plus y squared to the 1st power. Common error here is when you take the derivative of the inside, you don't distribute everything, which you would need to, right? The derivative of the outside times the derivative of the inside. So you need to put that maybe like a bracket to tell yourself, okay, I'm going to multiply this term to both the derivative of the inside. The derivative of the inside is going to be 2 terms. What's the derivative of x squared with respect to x? 2x, right? Plus, what's the derivative of y squared with respect to x? Very good. 2y times dy dx. Another common error in these problems is not differentiating y correctly. So do you see I have this term times the quantity of these 2 terms? So that's the derivative of the left-hand side. The derivative of the right-hand side would be 169 times 2x minus 169 times 2y dy dx.
169.
Yeah?
Wait, what's the, is it the derivative of 169? 0.
Yeah, so you could do it that way, but then you're taking the derivative of the inside. So you have 169 times 2x minus 2y dy dx, and then distribute the 169. This way, because every term has a 2 in it, I'm going to be able to cancel the 2. Any kind of cancellation you can do earlier on is going to make your calculations easier, right? Because if I say 2 times 198, that's just another number to hold on my calculator versus just 198. So does everyone understand this step? You can, if you have this step, it doesn't matter how you cancel. As long as you do everything correctly, you can get dy dx and plug in your x to be 5 and your y to be 1. Your numbers might be a little bit more complicated where you need to simplify it. So any kind of simplification earlier on. So here, if I divide through the whole expression by 2, I can just cancel all the 2's. Right? Because it's this times this times this, and this. They all have a 2 in common.
Would that 12 become a 6 then as well? Or is it,
What?
would that 12 become a 6 then as well?
It would not, because I have this term times this term, right? And this term times this term. So I'm canceling the 2 in this term and the 2 in this term, so the 12 stays the same. So now I can go ahead and distribute out. I have, okay, sometimes students will want to FOIL this. However, there's no need to FOIL it. I can just leave this term times this term times this term, and it's going to leave it more compact. So I have 12x, x squared plus y squared, plus 12y, x squared plus y squared, dy dx, equals 169x minus 169y dy dx. So now I have everything as term plus or minus a term. There's no multiplication in there. So now I need to solve for dy dx. So I'll go ahead and write multiple steps out. I have 12y x squared plus y squared dy dx. I'm going to go ahead and add 169y dy dx. That leaves me with 169x minus 12x x squared plus y squared. I could even pull out an x if I really wanted to. It's not horribly crucial. So dy dx equals 169x minus 12x x squared plus y squared over, I'm going to write it as 169y plus 12y x squared plus y squared. There's nothing to cancel. I could pull out an x, and then I have x over y, and then I would have 169 minus 12 times this number. However, at this point, it's not extremely important. X is 5 and Y is 1. So then I have 169 times 5 minus 12 times 5 over 26, or sorry, times 26, divided by 169 times 1 plus 12 times 1 times 26, right? 25 squared plus 1 squared. 5 squared plus 1 squared is 26. So these are just numbers. We could have possibly simplified here, you know, both of these have a 5 in it, and I could pull that out. And both these have a 1, I could pull it out. So then I would have 5 times the number, which would be a little bit easier to plug in my calculator, but this is not horribly difficult, right? So then going to my calculator, if I have 12 times 5 times 26, 169 times 5 minus this number gives me minus 715 over 12 times 26 plus 169, 481. 715 divided by 13 is 55. 481 divided by 13. Oops. 481 divided by 13 would be 37. So this is simplified, and they want your answer to be simplified. So this is your correct answer. Minus 55 over 37. On the final exam, I've seen an example like this on the final exam. This is worth majority of your points, and then you get like 1 point for plugging it in incorrectly. It's like, can you plug this in a calculator correctly? Can you input the right series of numbers in your calculator? This is where the work comes from, knowing the derivative. And of course, you could write this multiple different ways, depending on how you distributed and collected like terms. If I expand this out, I could have 12x cubed minus 12xy squared.
So the reason why you didn't FOIL it up there is because you're treating the 12 to the parentheses x squared plus y squared as one whole thing.
Yeah, as one
So
term.
then you just
So I did, you could kind of say I did FOIL it, I just left it factored, or I left it together, right? Because this is one term, and this is one term, and then this would be 2 more terms. So there is really 4 terms here, right? If I take 12x squared times x, that's 12x squared times x. And then 12y squared times x would be 12y squared times x. So that's here. I just treated it as one term. Right, so I'm taking this term times this term times this. So I can leave it like this because I just want dy dx. I could expand that all out and just have more terms. And that's perfectly fine. Majority of the time, students make a mistake in entering in the x and the y by plugging in their calculator wrong. Or the fact that they don't distribute the derivative of the outside evaluated at the inside times the derivative of the inside. Multiplication goes to the derivative of the inside. So if you have a product on the inside, use the product rule, it gives you a plus. You have to be very careful to distribute the derivative of the outside to both terms in the derivative of the inside. And then the rest is algebra. Maybe more, I kind of want to know, I kind of see where my answer is going to. I could simplify this as x over y, 169 minus 12, x squared plus y squared, over 169 plus 12, x squared plus y squared.
that's how the answer's.
Yeah, I mean, and then when I plug in my 5 over 1, I get 5 out here. I get some number up here and some number. It's going to simplify to the same thing. So yeah, this is what the answer has because they're factoring out common things. Because now when I plug in 5, I'm only plugging in 5 here and 5 here. And when I plug in 1, I'm only plugging in 1 here and 1 here. So I know this is 26. I know this is 26. It's the same thing. So this is just a number over another number times 5. But you should be able to get it get it with kind of hitting it with a hammer as well, as long as you don't break any algebraic rules. Question?
Can you do number 19 in the written homework?
On the written homework?
3.1?
So, number 19 on 3.1. Read, study, practice. 3.1. Number 19. So we have similar, except now we're plugging in maybe a little more annoying numbers, but it's still just numbers. So let's look at number 19 on 3.1 on the written homework.
What is that the mouse is over there? Squares. Square root of 3 over 2.
Yeah. So I'm looking for a circle centered at 0, 0 with radius 1, and I want to know the slope at 1/2 square root of 3 over 2 and at 1/2 minus square root of 3 over 2. So if I graph this, I have, and you can expect one to be positive and one to be negative, right? This is the problem. So if I plug in x to be a half, I either get plus or minus square root of 3 over 2. So you can kind of maybe know something about trig, know what this angle is to get a perpendicular line, and so you could kind of guess without actually doing the calculus. But safer to go about and do the calculus. So differentiating this function with respect to x, what's the derivative of x squared? What's the derivative of y squared with respect to x? What's the derivative of 1? 0. So I get dy dx equals minus 2x over 2y. So I get x over y minus, sorry, right? So the derivative with respect to y is minus x over y. So if x is 1/2 and y is square root of 3 over 2, I have minus 1/2 over square root of 3 over 2. If I flip and multiply, I have minus 1/3, right? Okay, sorry. Yeah, so forth, if the other one is going to be minus a minus, so you get 1 over square root of 3. Any other questions? Question?
If you wrote it as x plus y squared, does it change anything? Or does that help you out?
If I say,
If you took the derivative of x plus y quantity squared,
that would be different. Yeah, so I see, x plus y squared does not equal x squared plus y squared. Very common mistake, right? This equals x squared plus 2xy plus y squared, right? So the derivative here would be different. On the written homework, on 3.1. So number 11. So here there's just, as long as you don't do anything, this tangent one? Yeah, so there's the derivative of the outside evaluated the inside times the derivative of the inside, and you just go through there. So,
That's the one that was wrong.
yeah, if you look at the answer here, it's not correct with this plus, it should be multiplied. If you look at the student solution guide, the 3 point, if you look at the, where'd it go? Student table of contents, student study guide, student solution manual, 3.1 number 11, it has the answer correct. So this is the correct answer. The only thing different is they put a plus when they put it, embedded it into the book. So do you have a question about the answer being correct from seeing the answer or on how to do it?
Because the answer is like confusing.
So the answer is wrong if you look right from the book. This answer is correct except the plus should be multiplied. Okay, so let's look at this problem. This is number 11 on 3.1. So I have tangent cubed of xy squared plus y equals x, and you want to find dy dx. So what is the outermost function? The exponent. Something is cubed. What's the derivative of something cubed? Well, 3, that's something squared, right? So the very first thing I do is I take 3 tangent squared of x squared plus y. Okay, so let's say I'm differentiating this with respect to x. So I have this side, which is something cubed, and the derivative would be 3, that same something squared. Right? So that's the derivative of the outside times the derivative of the inside. So you have to be very careful with your parentheses here. So what's the derivative of tangent of something? Secant squared of that same something, right? So then I have secant squared of that something.
So you're not looking at the tangent to the third anymore, or the tangent to the second. You're just looking at the tangent since that's the inside.
Yeah, so on chain rule, you always start at the very outside function and work your way in. So the very outside function is something cubed, and the derivative of something cubed is 3 something squared. That something is the inside. You leave it totally alone. Then you take, okay, then it's the derivative of the inside. Well, the inside is tangent of something. So the derivative of tangent is secant squared whole to something times the derivative of the something. So the derivative of something is this function.
Excuse me, what in the 3 tangent square? Can we put a square root and
On the other side of the parentheses.
yeah?
You have to be very careful. You could write it as 3 tangent of xy squared plus y squared.
Yeah.
That's fine. But you wouldn't want to write tangent of xy squared plus y squared. You wouldn't want to write it like that. Because that's saying you're taking this, squaring it, and then taking tangent of it. So a lot of times that's why we move it over here. Because they're saying you're taking tangent of this and then squaring it. Okay, so does everyone okay with... So then, now I need to take the derivative of this function. So maybe a little bit early to put the bracket, but that's fine. So I'm taking this times this times this. So what's the derivative of the inside function? The product rule, right? So what's the derivative of xy squared?
Y squared.
Yeah.
1y
Y
squared
squared plus
plus
yeah.
Right? Plus y is a separate term. So the derivative of the xy squared would be here. And then the derivative of y would be there. So I have the derivative of the outside evaluated at the inside times the derivative of its inside evaluated at its inside times the derivative of the innermost inside, which is this. Once I get here, I'm done with the left-hand side. All that equals 1. So now I have to be really careful the way I write it because this whole term here is being multiplied by this term, and this term. Right? So let me end the bracket maybe. So it's saying, so this is just a term out front, right? A term times a term is a term. Times a term plus a term plus a term. So I have to distribute everything here would be distributed to all 3 terms here. So writing that, I would have times secant squared xy squared plus y. I might put a y squared here. Plus 6xy tangent squared of xy squared plus y times secant squared of xy squared plus y times dy dx. So running out of space here. Okay. Plus
Divided by all that?
what?
Could we not just divide it by
Um,
right off the bat?
Could you? You could, except then you're going to get more than one term, which is fine. You can do that because this doesn't have a dy dx in it. You could divide it all off that, but then you're going to end up with minus y squared term all by itself, and then you're going to have to divide all that by x2y plus 1. And you can't put it in as a fraction over fraction. You have to simplify it. So it's almost better to leave it all expanded and then simplify it in one step versus two. Okay, so then I have a plus that whole thing times dy dx, right? So 3 tangent squared xy squared plus y times secant squared xy squared plus y times dy dx equals 1. So when I multiply the first one, I get this whole thing times y squared. This whole thing times 2xy, so then I get 6xy times the whole thing, dy dx, and then the whole thing times dy dx equals 1. So I need my dy dx on one side, everything else on the other side, so I can subtract this whole term. The other two terms have a dy dx in them, so I have, I'm going to go ahead and write dy dx equals a 1 minus 3y squared tangent squared of xy squared plus y times secant squared of xy squared plus y divided by, if I factor out a dy dx, what I'm left with. So if I factor out a dy dx, I'm left with a 6xy tangent squared of xy squared plus y, secant squared of xy squared plus y, plus 3 tangent squared of xy squared plus y, secant squared of xy squared plus y. However, I can, in my denominator, I can simplify it, and your book probably does this. On top, I leave it alone. There's nothing I can do on the top. And on bottom, I can pull out basically a tangent squared of xy squared plus y times a secant squared of xy squared plus y, and then I'm left with a 6xy plus 3. Oops, sorry guys. Question?
Can we expect a problem like this being using it?
This one's a little intense, so probably not. Maybe something similar, but instead of tangent cubed, it's just tangent. Because then that's going to save you, a tangent squared in each one of these terms. And it's going to be a little easier to write it. Question?
I'm okay with like how you get the whole entire first part up until the point where you write dy over dx plus dy over dx.
Here.
Yeah.
So this comes from, you see the derivative of this one line is the derivative of x times y squared. Then I have plus y. What's the derivative of plus y? Plus dy dx. So the double line comes from the derivative of y, right? If I have a plus b and I differentiate that, it's the derivative of a plus the derivative of b, right? If I have a times b plus c, then I have to use the product rule on a and b plus just the derivative of that one term. So yeah, this one's just, after you get to the derivative, the algebra is somewhat annoying, but doable. It's just rearranging functions, which are just functions. Turns out, what's going on here is more complicated, but does that make sense? So if you look at the answer on 11, they even factor out a 2 or a 3. You wouldn't necessarily have to do that. Even the factoring step we did wasn't necessarily. Everything's correct except this plus. Should be multiplied. Any other questions? What's your question on? The second derivative? So have you done the written homework?
Yeah.
The Wiley homework on this problem? So if you notice, number 15 is a Wiley problem as well.
Yeah, I got that one right.
You did this one right, then you should be able to do the one in the written homework. You do the same process. You take the first derivative, simplify it. Simplifying is key here. If you have x to the fifth over x to the fourth, don't try to do the quotient rule. Simplify it as x, right? So then you're going to have the first derivative in terms of x and y differentiated again. When you take the derivative of y, you get dy dx. So then you have your dy dx to begin with and plug it back in. So a lot of these are similar to your written homework problems. So if you can do them on Wiley, you should be able to write them up. And just a comment, I don't know in this class if I've gone over just looking at the grade book. See, a lot of students are not entering anything for the first 3 attempts and going to the solution, and then trying to replace all the 3s with 5s from the. You're not learning anything by doing that. You're only cheating yourself. I could probably get my 3-year-old to do that. She doesn't mean she knows calculus. So don't spend your time by doing that because it's just wasting your time. Sure, you get the homework points, but homework points are 15% of your grade. It's not going to save you on a quiz if you don't know even how to start the problem. And the same thing with the final exam in the in-class exam. So you might say, oh, I have 100% on my homework, but that doesn't mean anything if you're using that method. So I know it can be kind of tempting where you want to get your full credit in before the due date, but that's not helping anyone. So my little spiel on that, just to keep that in mind. Okay, so I'm going to go ahead and start 3.4 today. 3.4, generally students don't enjoy this section because they're word problems, and it's related rates of change. So 3.4. So maybe some motivation. Generally, there's 2 application problems on the final exam. Being about 20% of the final exam are these application problems. If you don't even know how to start it, you won't get any points. There are certain steps you go through, and each step you go through, you get some points for, so your partial credit. So there are application problems, which personally I think, okay, that's some motivation of kind of neat problems, like we'll do related rates. You've already seen one with like the ladder leaned up against the wall, and it might be sliding down the wall at a certain rate. So there's 3 things that are changing. The only thing that's not changing is the length of the ladder. The height that the ladder is on the wall is changing. The distance, the bottom of the ladder is moving against the wall is changing. And then this angle theta that theta makes with the ground and the wall is changing. So I could ask for 3 different things. I could ask for dx d theta, dx dt, d theta dt, or dy dt, depending on what I name x, y, and theta. So related rates, the goal is this. You're going to try to find the rate at which some quantity is changing by relating the quantity to other quantities rates of change are known. So most of these problems, I give you everything you need to know in a form of a paragraph. And then you have to decipher what each of these rates or which of these things are named, put them in a relationship together, so some kind of function. A lot of times we use trig here. If you talk about majority of the problems we'll use trig, other one we might use Pythagorean's theorem or the formula for area or the formula for volume. So I might, if one of the ones I've seen before on final exams would be like an oil spill. A certain area of an oil spill is increasing or decreasing at a certain rate. If I'm pouring oil in water at a constant rate, at first my area affected increases a lot, right? Like you would say there's nothing there, and then all of a sudden I have this big puddle of water, or this puddle of oil on top of my water. But after a certain period of time, if the water remains constant, the oil spreading is decreasing, a smaller rate of change from the beginning. So it's all going to depend on the radius. And you can think of the same thing with blowing up a balloon. At first, if I start blowing up a balloon, the volume is changing really fast. And then after a certain point in time, if I'm putting in the same amount of air, you can't really see it expanding that much, that rate of change. So I will give you everything you need or the information to find the rates of change of everything in the problem except for one rate. And then your goal is to plug in everything else that's given and solve for the rate I want. So your book starts us off with a cone-shaped water reservoir. And this water reservoir is leaking at a constant rate. So I have water in here. And this is a certain height. And the volume is pi over 3 times the radius times the height. If it's anything other than like the area of a circle, you'll be given the formula. Like it might give you the formula for volume of a sphere if we use something like that. So here, the radius would be the distance, right? So up here's the radius, and here's the height. The height of the water. The water's, dripping at a certain rate. So now I might want to find the rate of change of volume of water. So again, it's going to depend on how much water I have in here. So to do that, we're going to differentiate this function. So if I want to find the rate of change of volume, I'm going to differentiate it with respect to time. So that's the important thing in this section is everything is changing with respect to time, not x. Volume is a function of time. If I let time change, the volume of water is changing, right? Every drop, the volume of water is changing. Well, with the volume of water changing, the height of the water is changing. So it's changing with time. And the radius of my top layer of water is changing, right? It's decreasing, the volume's decreasing, and the height is decreasing. So I would expect the rate of change to be negative. So differentiating this, what's the derivative of v with respect to t? Very good. dv dt. This is the derivative. So now I'm going to differentiate this with respect to t. I get dv dt. What's the derivative here? R is changing with respect to time, and h is changing with respect to time. So what's the derivative of r squared? 2r dr dt. So then I would have pi over 3 is a constant times 2r dr dt hold h, right? Because that's the second function. Plus hold the first function times the derivative of h. What's the derivative of h? dh dt. So this is what we're talking about here when we talk about relating one rate of quantity with other rates of quantity, rates of change. This is the change of volume. It's related to the radius at that given point in time, the height at that given point in time, the rate of change of the radius, and the rate of change of the height. So there's a lot of things we have to know to solve for dV/dt. Question?
The R and H in the picture, is that the radius of where the liquid is?
Yeah, so that would represent the, so if it was all the way filled up, it would be this H and this R.
Okay.
But we can only talk about it at some, so we're going to evaluate this at one instant in time. So if time is 5 minutes, so if this is all the way filled up, and we know it's dripping out at a rate of some volume, maybe 5 milliliters a minute. So after 5 minutes, we know the volume at that point in time. If we know the volume, we should be able to find the radius and the height. So it's going to be a specific radius, a specific height, and a specific dRdt and a specific dHdt based on what's given. So if they give us the rate of change of volume, how fast is this leaking out? That's the rate of change of volume. So you're going to say, okay, at time equals 5 minutes. Well, at 5 minutes, the water level is going to be at a height of given and a radius of given. And then you only need to know the rate of change of the radius and the rate of change of height to find dV/dt. And it turns out in this shape, the radius and height are related by similar triangles, all based on the height of the water. So you can write up a similar triangle. And we'll do an example of that. We're going to start at a little bit smaller problems. But do you see here how I differentiated? I wanted to do one at first where there's two different relationships, R and H, in the volumes and volume. So really there's three quantities that are changing. If I differentiate R, I get dRdt. If I differentiate H, I get dHdt. So the relative change here is a relationship of a rate of change of different quantities. So we don't have time to do an example, but we have enough time to kind of write up the strategies for solving the rates of change problems, and then I'll do examples tomorrow. So let's look at some strategies. Strategies for solving related rates. So the first step you kind of do without thinking, and that's assign values or assign letters to all quantities. So height is H, area is A, volume is V, radius is R. So you can get some kind of relationship to all these different quantities. Step 2 is to identify the rates of change, and the rates of change are going to be the derivatives that are given and the rate of change that is to be found. Okay, so first step is to set a letter to all quantities. The second step is to identify what's given and what needs to be found. Do I know the height? Do I know the radius at any given point in time? Do I know the rate of change of the height? Do I know the rate of change of the radius? What do I want? Do I want the rate of change of the height, the rate of change of the radius, the rate of change of volume? Step 3 is to write an equation that relates all the quantities. Honestly, this is the hardest part. If you don't have an equation, you can't differentiate it, right? So before, up into this part, I've always given you an equation and asked you to differentiate it and solve for dy dx or whatever. Here, I'm giving you some kind of information in the form of a paragraph, expecting you to come up with a relationship. So we've already kind of seen this example with the ladder problem. If this is theta, say maybe the ladder is 5 feet. If this is x and this is y, I could ask for the relative change of x with respect to time. Theta is changing with respect to time, x is changing with respect to time, and y is changing with respect to time. If you think of this ladder, it's being slid this way. If I pause it 1 instant in time, then I know that the a or the x, and I know the y, and that will be given. But I would also know the rate of change of x or the rate of change of theta to be able to find x. So I would give you this kind of scenario, and you would have to say, okay, I'm going to say sine of theta is x over 5. But I could also ask how fast is the ladder moving against the wall. Then you would have to use cosine of theta, which would be y over 5. Then once you have that formula, you differentiate it. So that's step 4. And that is to differentiate both sides of your equation. Step 5 is then, once you differentiate it, you plug in step 2's values for anything that is changing. So if my ladder is 5 feet, it's not changing. I'm going to use that in my equation to be 5. But if I say evaluate it when the ladder is 2 feet high against the wall, you don't plug that 2 in until you after you differentiate it, because this is changing with respect to time. Theta is changing with respect to time. Y is changing with respect to time. You leave that as a variable. The only thing that's not changing with respect to time is 5. The length of the ladder is a constant, 5. So this is another important step, is you wait until you differentiate to plug in the quantities that you found in step 2. And then step 6 would be solve for what's asked. Solve for the rate of change that was asked for in the problem. So you might get a, dv dt equals something, but I might ask for dh dt. So then you just have a relationship, an algebraic relationship, and you solve for everything and get dh dt on one side. So we'll do some more examples. Well, we'll do an example of this on Tuesday and some more examples of that. So I'll see you guys tomorrow.